when we talk about the cosmology and quantum mechanics, so one thing that we have been hearing for a very long time, and you have used that term in uh, in explaining these phenomena also, which is quantum gravity. So what's the meaning of quantum gravity? And as we have heard that gravity depends on mass, and at quantum level there are not that like uh, very little mass is available, so gravitational force will be if I talk about in a layman language, that will be a very little force. So why are we talking about this thing, quantum gravity, and what exactly quantum gravity is? Are we understanding it in right way, or there's something different that is quantum gravity?
No, so in one way, it is a quest in physics because we know that we live in a quantum world, right? That may have been some kind of a folklore or to the common public, it may have been some exotic phenomena, but slowly these are becoming part of life. I mean, many devices are coming up which uses quantum mechanics very important. Similarly, the whole fact that the universe or space time itself bends under gravity is again something exotic for the common man. So where do you see them together? Okay. Now, for example, the latter one, this generativity, which describes this, dynamics of space-time responding to matter. Those effects are important for the Earth, for things around the at the level of 10 to 1 minus 9. So one part in billion or 10 parts in or one part in 10 billion, right? But when you are using your GPS to move from one to the other, these corrections have to be made. Otherwise, flights will crash. If you suddenly, if you someone in the GPS thing said, "Oh, I don't care about GRF, these subtle gravitation effect," and take them out, there'll be disaster in common life, right? Similarly, the devices that we are using to detect these, so for your phone, cell phone, and all, see, slowly you're using devices that depend on quantum mechanics. So we know that quantum mechanics is important, right? And not only important because you're building devices on that. So these are both things we know that the universe is quantum, and we also know there's gravitation. The biggest challenge is we have been able to quantize electromagnetic forces, weak forces, strong forces, and we have a very consistent picture of the classical electromagnetic force and how to quantize it, or the classical strong force, how to quantize. That has not happened for gravitation, and it's kind of slightly technical as to why it doesn't happen. So I won't get into that, but that remains the challenge. And there are approaches to it because see what happens is with gravity, the arena itself. So every other interaction, you have a space time in which you work. The space time is a background thing that is there. With the space-time itself, you'd like to think of it as discrete. So there are approaches which look at atoms of space and space-time, right? And various kinds, very, there's a not. It's not as if you're breaking up space-time into lattice, but there are different carbs
So
in
are
which
we
this is
are
done.
we talking about like the smallest entity of space time, like
Yes,
what we call atom as the smallest entity
yes,
of matter?
right.
Okay, okay,
So
okay.
same way, the scales, and this happens at the level of what is called the Planck scale. So you have to put 19 zeros, point and then 19 zeros and then a 1 meter. So that takes you to Planck scale. Okay, these are something that we don't expect to encounter anywhere in daylight. So even if there is something granular at that level, the normal things or even the highest energy explorations that we have done is not capable of exposing that. However, this has again they could have a big implication for the beginning of the universe, because we know that if it had gone to, you know, 10 to 16 GeV, it would have gone to 10 to 19 GeV. By the way, I think I got this wrong. So this Planck size is 33 zeros, not 16. In energy, it is 10 to 19 GeV. But if you wanted to talk about meters, it's 10 to a minus 33 meters, which is, 33 zeros, then you put a one and meter, right? So this is like scales that are not, explorable. Typically when you want to see small things, you have to use higher energy to see, right? So if you want to probe, say a bacteria or something on the micron scale, we use optical telescopes. But you know that when we probe further the crystal structure of a object, we use X-rays. So, you need to probe with higher and higher energy photons. But to probe something at 10 to a 19 GeV, the energies have to be that high of interaction to probe it. And there's no way we would do it in laboratory. So the universe, fascinatingly enough, I mean, if you think, it's amazing that the universe somehow has a way by which naturally it gives you a window to its entire history, right?
Oh,
Starting
okay.
from the earliest energies.